All right, in this section, we're going to talk about solving systems of linear equations, specifically when we have two variables and two unknowns. So we call that a 2x2 system. The two most common algebraic methods that we use are substitution method, and then what's sometimes referred to either linear combination or the elimination method. Okay, there are a few other methods that are less common, and we will learn these later on in the chapter, one called Cramer's rule, and then through matrices, where the 2x2 name will also make more sense when we talk about matrices. Okay, for now though, we're going to focus on these two for today's lesson. The other part we're also going to review that you should have learned in Algebra 1 is talking about solving systems of equations graphically. So when I have something that has two unknowns, like y equals 1/2 times x minus 2, there are two unknown variables in here, y and x. And if I'm looking for an exact solution, like one possible solution, if even possible, you need a system of two equations to find two unknowns. Okay, and so over here on the left, we're given our two equations, right? Two equations with two unknowns. We're going to be able to try to find an exact solution. And basically, I want to find the value of y and x that makes this entire system true. So let's start by first just graphing this equation of a line. It is in the form y equals mx plus b, okay, where b is our y-intercept down here at -2. And then, of course, we can think of this as our rise and run for our slope. So my rise is +1, so up 1. My run is +2, so right 2. So up 1, right 2, up 1, right 2, or continuing to the left on my graph, down 1, left 2, and down 1, left 2. Okay, so we should have a line that goes through all of those points, and I completely missed, but we'll give it another shot. Pretty close, pretty close. Okay, we're getting closer. All right, we'll go with that one. So here's our line, our first line. And keep in mind that every x and y coordinate on this line makes this equation true. When I plug in an x value of 2 and a y value of -1, each side of the equation, those two sides of the equation are equal. Okay, every point on this line represents something that makes this equation true. Okay, let's graph our second one. We're going to do this in a different color. We'll use green here. Again, y-intercept is at 4. My slope is up 7, right 2. Well, up 7 is a little off my graph. So rather than going up 7, right 2, let's go down 7. 1, 2, 3, 4, 5, 6, 7. And left 2. And lo and behold, we have a point of intersection. Okay, so here's approximately my other line in green. And every point on the green line, including the ones, right, that are nice integer points, every point on here represents something that makes the second equation true. And what I'm looking for is what value or values make both equations true. Well, of course, we can tell by looking at our graph, the one point that makes both equations true is our point of intersection. Okay, so this point of intersection is the solution to our system of equations. So we're going to find its coordinates. My x value is -2, and my y value is -3. So we do write our solution to a 2x2 system as an ordered pair. That's when x is -2 and when y is -3. So that is our answer. Okay, so this is solving a system graphically. We can graph the equations and look for point or points of intersection, okay, if they exist. Okay, whoops, we don't want those back. Let's do this. Our next example. Okay, these also happen to be in y equals mx plus b, so we'll graph these a little faster. For my first one, my y-intercept is -4, and my slope is down 3, right 1. Down 1, 2, 3, right 1, or going in the other direction, it would be up 3, left 1. Up 3, left 1. Up 3, left 1. Okay, so there is our line for our first equation. Now we need to graph our second one, and we're looking for where they intersect. So my second one has a y-intercept at -2. And it has a slope that follows the same pattern, -3. So down 3, right 1, down 1, 2, 3, right 1, or up 3, left 1. 3 left 1, up 3, left 1. And of course, hopefully we're now recognizing that these lines are in fact parallel. We have a set of parallel lines. And one thing you hopefully remember from geometry about parallel lines is they never intersect. So if every point on my blue line makes this equation true, and every point on my green line makes this equation true, where would I find x and y values that make both true? Nowhere, right? They never share any x and y values, so this system has no solution. Okay, so that is possible that when I'm trying to solve a system of equations, there might be no solution. Okay, there is a third case that I'm not going to be doing graphically yet, but we'll talk about later, and that's when the lines are the same line, essentially. Okay, so they're called concurrent, but if these lines end up graphing right on top of each other and it's the same line, we have infinitely many solutions. So we'll talk about that when we do some algebraic solving in a minute. Okay, so let's talk about the substitution method. So a couple of these problems are already set up for us. Our first one here is set up for substitution, and substitution is a good option when at least one of our variables is solved for, like positive 1y equals something. Okay, so in this case, y is solved for. Y is equal to this expression. We can use that. If this is what y is equal to, then in any equation that involves y, like say here, we can substitute our expression in. So what we're going to do is come up to this top equation that's -7x minus 4 times y. But in place of y, we're going to plug in our expression that we were given from the second equation. Y is equal to -5x plus 7. Okay, so you'll notice we just went from 2 equations with 2 unknowns to 1 equation with 1 unknown, right? In this case, I just have x as my only unknown variable. It is in a couple places, so we'll need to combine them here. But we did get down to 1 equation and 1 unknown. We're going to be able to solve for the x-coordinate in this equation. So let's go ahead and distribute. We do have a -4 to distribute into our parentheses. So we have -7x, just drops down. -4 times -5 is positive 20x. -4 times 7 is -28, equals -2. Well, let's combine some like terms here. Okay, these two together make 13x. And because I'm going to want to get x by itself, let's go ahead and add our 28 to the other side. Save myself a little bit of writing. So we get 13x equals 26. Well, I can finish solving for x by dividing by 13, and we get x equals 2. Okay, so I've got the first part of my answer, but remember, like from our graphing, I know the x-coordinate where these two lines cross. And by the way, if you do get a solution for one of your variables here, we don't get like some weird algebra happening that we'll talk about later, that does mean there is one solution. So let's find our y value. And the easiest place I can plug in, remember that's where both of these equations are the same. So it doesn't matter which one I plug into. We should get the same y value back if we got the correct x. So you get to pick whichever one you plug into here, but I'm going to go with the one that already says y equals. Seems to make sense. Y equals -5 times x plus 7. So we're going to substitute in our 2 that we just found, and of course calculate this out. -5 times 2 is -10, plus 7 makes -3. So our solution here for our system, and again we will write this as an ordered pair for our final answer, is positive 2 and -3. That's my x, that's my y. You don't necessarily have to label those, but they do need to be in the correct place. Okay, so there is the solution to my system. Let's try number 4, which is also set up for the substitution method. This particular one, both equations say y equals. Well, in fact, this actually makes my life a lot easier. Let's say if I know y is equal to this expression, then in any other equation that has y, like up here, I can replace it or substitute in 5x minus 13. So in fact, I can just write 5x minus 13 equals 3x minus 5. You guys might also remember the transitive property that if y is equal to this expression and y is also equal to this expression, then these two expressions have to equal each other. So you can think of the transitive property. Okay, well, hey, we've got an equation with just x in it now. Let's use that to solve for x. So let's put our x's on one side. Let's move the constants to the other. Okay, so this gives me 2x equals negative 5 and 13 will make 8. And dividing by 2, we get x is 4. We've got our x coordinate. Okay, so just like before, I can pick either equation to plug into. As long as I've calculated the correct x, it doesn't matter which equation I plug into, right? They should be intersecting at this point, so they should have the same y value. So I'm going to use the one up top. It looks a little easier. 3 times x minus 5, maybe slightly easier numbers to calculate. And we're going to plug in positive 4. Okay, so we get 3 times 4 is 12, and 12 minus 5 is 7. Okay, you don't necessarily have to box in x and y, that's just for your visuals here. But our final answer, again, we're going to write as an ordered pair, is 4, 7. That's my x, that's my y. And if we were graphing those two lines, that's the ordered pair, or the point where they would intersect each other. All right, here's a good time to try a couple problems that are very similar, but see if you feel confident in substitution. So try these two out. You can pause the video now, write them down, and solve it, and then I will have the solutions up in a second. All right, here are our answers. For 5, you should have gotten 4, 0, and 6, both x and y are negative 2 and negative 2. Okay, if you didn't get those, or you're not sure my work, you can pause the video to look through it here, or you can ask questions in class. Okay, let's look at some more problems. This time we're going to look at using the elimination/combination method. So we're going to be combining these two equations together into one. Sometimes you can call this addition, like we're going to be adding equations. You can actually add equations together. It's a terrible line, but hopefully you get the idea. You can add them together and combine like terms and create a new equation. So we'll actually use that a lot. So this is my personal favorite method. And again, one of the things that we're going to be able to do here is try to combine our two equations. And luckily for us, this first equation is actually set up to where if I were to add them together, notice what's going to happen with my y values. I have a positive 5y and a negative 5y. We're literally going to add like terms here. So I think this is already set up to eliminate one of our variables. Okay, we want to combine them so that we eliminate one of the variables. And if they're not set up to cancel each other out right away, we'll talk about how to do that in some of our other problems. But let's try this. So right now, these are set up to where if I added them, we'd get a positive 2x from 9x and negative 7x. My y's essentially cancel each other out, so we have no more y's. And negative 16 and 8 make negative 8. And check that out. Now I have an equation, 2x equals negative 8, where I can solve for x. Divide by 2, and I now know the x-coordinate of my system is negative 4. Okay, so I've got one of the coordinates, and like the substitution method, we are going to substitute in to find our other one. Okay. You don't have to substitute in, but it's probably going to be for the best. So we can really use either equation here. I'm just going to use the top for convenience. It doesn't really matter. So 9 times x plus 5y equals negative 16. So we're going to substitute in the x value we just found of negative 4. And again, remember, it doesn't matter which equation you plug into. We should get the same value back for y. So let's multiply. That gives us negative 36 plus 5y equals negative 16. Add 36 over. That gives us positive 20 on the other side. So now I have 5y equals positive 20. And dividing by 5, we get y equals 4, positive 4. Okay, so we've got an x-coordinate of negative 4, a y value of positive 4. So our solution to our system is negative 4, 4. There's my x, there's my y. This is my personal favorite method because, as we'll see in some later examples, with our other method, you don't have to plug back in a fraction. You can just, instead of eliminating y and solving for x, we can go back and eliminate x and solve for y. I also like doing that because if you got one of the answers wrong, it doesn't mean you got the other coordinate wrong. You kind of solve for them independently, which is kind of nice. Okay, so let's try our next one here. This time, it's not immediately set up. If I were to add these equations together, nothing's going to cancel out right away, right? Hopefully we see, yeah, that would just give me negative 6y and negative 10x, and we haven't eliminated either of my variables. So one of the other things we're allowed to do is we can modify an equation, right, for properties of equality by multiplying or dividing on both sides by the same value. So if I want to eliminate either x or y, and I think y is going to be easier, I just really want one of them to be positive 3y, right? That way positive 3y and the negative 3y in the bottom, they'll cancel out when I add them. So what we can do is take the top equation and multiply it by negative 1. Okay, so we can multiply the entire equation by negative 1, which gives me positive 8x, positive 3y, and don't forget you do have to do it to both sides. This becomes positive 28. So there's my new equation. Okay, now the second equation we didn't change. I'm just going to rewrite it so it's right below it. And now we can think about adding these equations together. Okay, so if we add these guys together, I'm going to end up with positive 6x. My y's are going to cancel each other out. So no y's there, equals, and 28 plus 2, don't forget to add these, give you 30. So dividing by 6, we've got our first coordinate. Our x-coordinate of where these lines intersect is 5. We can also solve for y by, instead of doing substitution like we did in 7, we can do elimination a second time. So this is an alternate way to get the second variable here. Okay, so what if instead of canceling out my y's, I want to set it up so that I can cancel out my x's? Okay, well, multiples of 2 and multiples of 8 could first meet at 8, actually. So I want one to be positive 8x and one to be negative 8x. So since I already have a negative 8x up top, I would need to multiply this by negative 4 throughout my entire equation here. So that would give me positive 8x, positive 8x. That would give me negative 4 times negative 3 is positive 12y, and negative 4 times 2 makes negative 8 on the right. So this is my new second equation when I multiply both sides by negative 4. And this is the original top equation where nothing is changed. Okay, so we're going to add these together. So we're doing elimination, but this time we're eliminating x. We've set it up so my x's cancel. And I end up getting 9y equals negative 36. And if you divide by 9, we get that my y-coordinate is negative 4. Okay, again, if I had just taken 5 and substituted into one of these equations for x and solved for y, right, taking this and use substitution like we did in number 7, you should get the same exact answer. But I like showing that you can just eliminate each variable. And the nice part about doing elimination twice is, let's say I did a calculation and I got this wrong. If I substituted back in a wrong number, of course my other coordinate's wrong, right? They're both wrong. Whereas elimination, if I mess up a calculation here, that doesn't necessarily mess up a calculation here. So I can at least get one of the coordinates right if you do double elimination. All right, so let's take a look at these next two examples. The first thing I notice about example 9, it does look nice and set up for this elimination method where x and y are each on one side. And it would not be easy to get x equals or y equals by themselves like in the substitution method. So I would first look at my variables and try to figure out which one would be easiest to eliminate, since if I were to add them, those won't cancel and those won't cancel. So I'd look at my values 4 and 7, multiples of 4 and multiples of 7. I don't think they meet till 28, which means I would need to multiply both equations. Multiples of 4 and multiples of 5 don't meet until 20, and I would also have to multiply both equations. So I think either way, we're going to have to change both equations here to eliminate one of our variables, and that's fine. It doesn't matter which. Let's go ahead and let's multiply each. Let's say I want to eliminate y. Okay, so I want to make these each meet at 20, and I want one to be positive 20 and the other negative. So this top equation, I'm going to go ahead and multiply by 5. Okay, so multiply it by 5, and let's write our new equation underneath. So 5 times negative 4x is negative 20x. 5 times 4 makes positive 20y. And 5 times negative 8, don't forget to multiply the other side, is negative 40. So there's my new first equation. Okay, our second equation, we need to multiply by 4. Okay, again, I'm trying to get this one to be negative 20, right? I've already got a positive 20y. And I like that it already has a negative sign. That's nice. So I don't need to multiply by a negative number. Like if this was positive, maybe I'd have to multiply through by negative 4. Okay, so multiplying our 4 through, I get positive 28x, negative 20y, and 30 times 4 is 120. So now we can go ahead and add these two together. So we'll do our elimination / combination here, where my y's are going to cancel. I get positive 8x equals 120 minus 40 is 80. And dividing by 8, we find that our x coordinate is 10. Okay, so pretty nice there. We can either, again, substitute in. Not a bad option here. And in fact, knowing that if I wanted to instead eliminate x and solve for y, I'd have to change both equations again. That sounds like a lot of work. And since I didn't get an ugly fraction or something that I'd have to substitute back in, I think maybe the substitution option like we did back in 7 is probably better to find our other coordinate. So let's go ahead and I'll just use the top equation. The numbers look fairly simple. Negative 4x plus 4y equals negative 8. And we'll substitute in our x coordinate we just found of 10 for x. Okay, so multiplying, we get negative 40 plus 4 times y equals negative 8. Add 40 to the other side. We get 4y equals 32, positive 32. And then dividing by 4, we get y is equal to 8. Okay, so we found our solution to this system is 10, 8, both positive numbers. So the solution to our system is 10, 8. Okay, let's try our next one over here. Number 10. It does look like, in fact, I can see that it's set up for our combination method already. And if I were to add them together, I like this. It's pretty nice. Our 8y's will cancel out. So let's just go ahead and directly add them. My y's are going to cancel. I get negative 2x equals 9. 7 plus 2. Ooh, well, when I divide by negative 2, I get negative 9 halves, or 9 over negative 2. But the overall fraction, negative 9 halves. Well, that could be pretty ugly to plug back in, right? If I plug in negative 9 halves there for x, I got to multiply it by 3. Then I got to move it to the other side and combine it with 2. And we got to find common denominators. That sounds like a mess. But that's where doing elimination a second time would shine. So we just eliminated y to solve for x. Let's try to find a way to eliminate x and solve for y so I don't have to do a lot of fraction work. Okay, well, I look at the values for x. If I want these to cancel out, they're first going to meet at 15. So I want one of them to be positive 15x and the other to be negative 15x. So I'm going to go ahead and multiply the top equation by 5, which would give me 15x minus 40y equals 10. Okay, so all of those values are multiplied by 5. Now I like that this already has a negative sign with it, so that makes my life a little easier to get my negative 15x. And I'll need to multiply that by 3 to make negative 15x. So multiplying that entire equation by 3, I get negative 15x plus 24y equals 21. And we can now add these together. My x's, of course, are going to cancel. This time I get negative 16y, I believe, equals 31. Oof, we're getting off the screen here. 31. And dividing by negative 16, we get negative 31/16. Pretty ugly value. Okay, so our solution to our system has some pretty ugly fraction coordinates. So these lines do cross each other, just not at nice whole number values. They intersect at negative 4.5 or negative 9 halves and negative 31/16. So some rather ugly looking coordinates, but they do intersect. There is one solution, and we found it here. And this, again, if you don't like doing a lot of work with fractions, like multiplying, adding, and subtracting is especially the worst part, then maybe doing substitution or, elimination to eliminate the other variable is the better option. Okay, we'll go over several examples of the ones in the previous slide in class. Let's also talk about our special cases. So we saw when we graphed, way back in the first slide, that if we graph these, we might get something like parallel lines, which has no solution. We might also get the same line, called concurrent lines, which would give me infinitely many solutions. So how do I know what case I have if I'm trying to solve algebraically? So let's say I wanted to solve this system, and the way it's set up, it looks like elimination is probably a good way to go here. My x's and y's would not directly cancel each other out, but I think if I multiply this by negative 2, I can make my x's meet at 6x. So that would give me negative 6x plus 12y equals negative 26. Okay, so we multiplied everything in that top equation by negative 2. The bottom equation is unchanged, so I'm just going to copy it. Equals 24. And now we're going to add them together. So let's add these things together. And we end up, okay, my x is canceled. That's what I wanted it to do. But, uh-oh. My y's canceled too. I didn't mean for the y's to cancel. They just did. And I get 0 equals negative 2. So what does that mean? If all of my variables cancel out, that tells me we have one of two things. We either have parallel lines, which means there's no solution, or we have the same line, which means there's infinitely many solutions. Okay, so these are the conclusions for each of those. So what does this tell us? Well, it tells us we have one of those two cases. It's either no solution or infinitely many. Okay. And here's how we tell. We look at this expression, and all we need to judge is it a true or false expression? Does 0 equal negative 2? No. If this is a false expression, that means that there is no solution. In fact, you could do a little algebra with those two equations to figure out that they have the same slope but different y-intercepts. This is, in fact, like parallel lines if you were to graph them. Okay, so let's try our next system over here. I noticed that my x's and y's would not cancel out right away if I tried the elimination method. But I think if I multiply maybe the bottom by -2, we could make our x's cancel. So let's do that. Multiply everything in the second equation by -2 gives me -12x, positive 18y, and positive 18. Okay, so that's my new second equation. The top equation is unchanged. And now, if I add these guys together, we can solve for our first variable. And my x is canceled, which I planned in. Oh, my y is also canceled. So we know we have one of these two cases. So I get 0 over here, and positive 18 and negative 18 also cancel and make 0. And as you can tell, this time we have a true expression. I guess over here where I said false, I probably should have I should have written false. Over here, this is a true expression. 0 does equal 0. And so instead of meaning there is no solution, it means there is infinitely many. So this has infinitely many solutions. And those solutions are the points on that line, right? It's really the same line twice. And so where do those two lines share points? They share them everywhere, right? If here's one line and the other one gets graphed right on top of it, they share points everywhere, right? So there's infinitely many solutions and they exist on that line. All right, our next one here, we have a word problem. Don't worry, it's not too bad. It says Danielle's school is selling tickets to a play. On the first day of the ticket sales, the school sold 6 adult tickets and 3 student tickets for a total of $96. The school took in $146 on the second day by selling 8 adult tickets and 7 student tickets. Find the price. Okay, so here's what we're looking for. Find the price of an adult ticket. Yes, that's one thing we're searching for. And find the price of a student ticket. Okay, so we're solving for two different things here. The price of an adult ticket, and let's define some variables. Let's let x represent the price of one adult ticket. And that's what I want to find. And I like very specifically defining our variables here. And let's let y represent the price of one student ticket. Apologize for my writing. Okay, well, let's see. To solve for two unknowns, we need two equations. So they have to have provided us enough information to set up two equations relating x and y. Okay, it's the only way to get an exact solution if one exists. So let's read through here and see what we figured out. On the first day of school, or of ticket sales, the school sold 6 adult tickets. Okay, well, they sold 6 adult tickets. So adult tickets are X. They sold 6 of them, right? 6 times the price of an adult ticket would tell me how much we brought in from adult tickets. They sold 3 student tickets. So 3 times our price for student tickets. And I know that together, right, the money we made from adult tickets and student tickets together was equal to $96 that day. So 6 adult tickets, 3 student tickets. When I add those prices together, that should give me $96. So likewise, it told me the school took in $146. So the amount they made was $146. And they got that by selling 8 adult tickets and 7 student tickets. My color didn't change. 7 student tickets. And we know together, the amount of money they made for each of those together made the $146 they brought in the second day. Now, all right, here we are. So I chose the elimination method because it would not have been easy to get x or y solved for by itself to use substitution right away. And I chose to eliminate x. So I made 6 and 8 meet at 24. And to make one of them -24, I chose to multiply the top equation by -4. Okay, so here's my new system, multiplying the top by -4 and bottom by 3. Canceling out x's, I got 9y equals 54 and y equaled 6. We got a pretty nice answer. So that meant, remember, y is the price of one student ticket, so $6 for one student ticket. Now, rather than doing elimination again, because I would have to eliminate both y's to solve for x and change both equations, and we had quite big numbers here, I chose substitution, especially since we had a relatively nice number to plug back in of 6. So I used the top equation, plugged in 6 for y, and solved for x, which gave us 13. So $13 for one adult ticket. Okay, we will see some problems with decimals and some more fractions as we work through problems in class, so make sure you're there for